Hey there! Quick question. Is this your phase when you've just added a new index but your query is still slow? Or maybe you've just created a new index and you notice that it's not being used? Maybe you don't know your indexes. Well, then you're up for a treat with this presentation. Welcome to Indexes Demystified. In this fast-paced mini-course, I will reveal all of the secrets of indexes. You will get an answer to your most burning questions, such as, what the hell is an index anyway? And what are the building blocks of indexes and tables? We will also completely dissect a query lookup, and we will look at the weaknesses of indexes and the quirks of indexes. Let's start with digging deeper into indexes. What is an index? Basically, an index is a complex data structure which keeps a copy of the indexed data. So if you would have a column called first name and you have an index on that column, that means that the index holds a copy of every first name entry. So an index definitely uses storage space. An index also keeps its data logically ordered. Why is that? It's because logically ordered data has a predictable position. Imagine that you would alphabetically order that first name column. Then you would know that you would find an Alex before you would find a Cletus, right? Having a logical order really helps when looking for something. And that's exactly what an index does. It helps to find data fast. So if we summarize all of this into a somewhat of a definition, then I would say that an index is an ordered data structure which helps to find the record faster in a table. If you could use a microscope to look at tables and indexes, you would see something like this. This is what tables and indexes are made of, and it is called a database block or a page. It is the smallest storage unit in a database, usually a couple of kilobytes big. It can contain either table data or index data. All of these blocks are equal in size, and a database tries to stuff as many data entries as possible in such a block. Indexes use these database blocks to build up their structures. So an index is a complex data structure. Basically, an index is just a B tree. I know what you're thinking, but that's the wrong kind of tree. A B tree stands for a balanced search tree. Yes, that's more like it. I don't understand why the short name for a balanced search tree is a B tree, but on the other hand, if they would have picked BS tree, people might just assume that it was bullshit anyway. Whoa, time out! Remind us, what is a tree structure again? So a tree structure is a hierarchical structure. And like many other hierarchical structures, it has one point of origin, which we call a root node or the root. Something like this. Like any other tree, it has branches, like these, and the elements at the end are what we call leaves or leaf nodes. So a balanced search tree is a special kind of tree structure. And what's so special about it? Well, in a balanced search tree, all of the leaf nodes are at the same distance from the root. So this is a bad balanced tree. This is a good balanced tree. As you can see, all of the leaf nodes are one hop away from the root node. You can imagine that updating a balanced search tree comes with a bit of an overhead because you want to preserve the balance. Otherwise, you lose all of the abilities of a balanced search tree. So why would you pick a balanced search tree as the base structure for an index? What are the abilities of a balanced search tree? Well, suppose you would create an index by using a balanced search tree. Then you would put the indexed data in the leaf nodes, and you would pair that data with the address of the original rows. If you do that, then all of the indexed data is at the same distance from the root, remember? And the root is where a lookup would start. So basically, every indexed value gets the same lookup time because they are at the same distance from the root node. That's the first superpower of a balanced search tree. Furthermore, a balanced search tree grows really slow in height, but grows faster in width, which means that you can add a whole bunch of new items before there is an extra level needed to hold all of the data. That's really important for the lookup time, right? So now that we all know what a balanced search tree is, we can continue with the structure of actual indexes. Behold, a visual representation of an index. From now on, I will call this the index tree instead of calling it a balanced search tree every single time. And you might have already guessed it, but every single node of the index tree is actually a database block or a page. Remember what a database block is? It's the smallest storage unit of a database, and it's what every table and every index is made of. Now, when you look at these leaf nodes, you might get the impression that they are connected somehow, that they are linked. And you are right. The leaf nodes of an index tree, they form a doubly linked list. Now, this is really important, so pay attention. Leaves that form a doubly linked list, that basically means that every node knows which node comes before it and which node comes after it. So that also makes that leaves are logically ordered on two levels. The first level is inside the blocks themselves. So in the first level is right here. As you can see, this data is ordered in ascending order, which means from low to high. Now, the second level of ordering is on block level. So that means that the block that contains the data 1, 2, 3 will always be right before the block which contains the data with 4, 5, 6. And this block will always be right before the block which contains the data 7, 8, 9. Why is this logically ordering so important again? It makes it so that every element has a predictable place. So whenever you get to this node, you know that all of the lower values will come before it and all of the higher values will come after it. This is what they call the leaf node chain. And this is the heart of every index. Let's get used to how indexes actually look like by going through some examples. This is an example of an index based on an auto-generated primary key column. As you can see, the leaf nodes contain all of the column values, as well as a reference to the entire row. Also, something that you need to understand about the index tree is how it's built up. Every parent branch or every parent node contains the highest values of their child nodes. So let's take an example here. This parent node contains number 12, 15 and 18. So the 12 is the highest value of this child node, the 15 is the highest value of this child node, and the 18 is the highest value of this child node. Alright, next example. This is an index based on a non-unique integer value column. So again, the leaf nodes contain all of the column values and they also contain a row ID which is actually a reference to the entire row. There's something cool about an index on a non-unique integer value column. That is, because of the ordering, the identical data is actually grouped together. You can see that right here. Here we have a couple of number 3s, a couple of number 10s, and at the end there's a pack of number 43s. The next example is an example of a composite index. A composite index is an index which spans over multiple columns. In our case, the first column is a non-unique value column and the second column is a unique value column. I'm going to refer to these columns as the department ID column and the ID column. Now when you look at the leaf node chain, you will find all of the values of the department ID column right here, and you will find all of the values of the ID column right here. Now because a composite index spans over multiple columns, there is a need of an ordering priority. You remember that all of the values in an index are ordered, right? So we need an ordering priority, and it's from left to right. So that means that the values of the department ID column, which is the left utmost column in the index, will be ordered first, and then all of the values of the ID column. And this has some interesting side effects. Because of the ordering priority, all of the values of the department ID column are globally ordered throughout the leaf node chain. So that basically means that you will find the lowest department ID value in the first leaf node, and you will find the highest department ID value in the last leaf node. The second side effect is the fact that the second column ordering is relative to the values of the first column. So that means that the values of the ID column are not globally ordered. You can only see an ordering in the ID values whenever you have identical department ID values. You can see that right here with all of these number trees. So here we have identical department ID values, and then you can clearly see the ordering of the ID column. But then the next department ID value is number 5, and then we have number 9, which isn't ordered at all globally over the leaf node chain. It's really important that you understand that. So now that we all know what an index is and what an index is made of, let's focus on lookup and start answering the lookup questions. So we've seen all of these structures that form an index. How are these being used when doing a lookup? And what's the process of a lookup? Have no fear, when you look at a lookup with an index, you will soon find out that it's just a fairly simple 3-step process. Let's have a closer look. So the first step of a lookup with an index is traversing the B tree or the index tree, right? We've seen plenty of examples with that index tree, and you traverse it until you reach the leaf node chain. Then the second step is following the leaf node chain until you have selected all of the possible results. And then the third step, when you have selected all of the possible results, then when necessary, you can access the table data and form the actual result that will be returned. What exactly happens when a lookup is traversing the index tree? Well, a lookup starts from the root, and then it goes over each value in the root node in ascending order, and it evaluates all of those values with the following function. Is the value in the node greater than or equal to the value that we're looking for? If so, then the lookup follows the reference to the next branch. And this happens until a leaf node is reached. Now this may all seem a bit abstract, so let's look at some examples to straighten this out. This first example is about an index on a unique key column. We have a table called employees, and the index is on the ID column. What you're looking at right here is the top half of the index tree. For this simple example, we will only need the top half anyway, and it's a bit zoomed in so that you can follow along easily. So when we want to execute the query select everything from employees where ID is 3, what happens? Like I said before, we start at the root node with the lowest value. Every single one of these values will be evaluated with a greater than or equals function. So this is how it goes in detail. Is 9 greater than or equal to 3? Yes, it is. So we have a positive match, so we follow the reference to the next node. In the next node, we start here at the lowest value again. And we have the following evaluation function. Is 3 greater than or equal to 3? Yes, it is. Boom, we have found the leaf node. And that's all there is to it in this simple example. The next example is an example with a composite index. This index spans over 2 columns, being the department ID and the ID column. What you're looking at right here is the bottom part of the index tree, which is also enlarged a bit so that you can follow along quite easily. In this lookup, we want everything from the employees table where the department ID is 43 and the ID is 20. As with any other lookup, we start at the root node with the lowest value, which is right here. So the first evaluation function is going to be, is 10 greater than or equal to 43? No, it is not. The same for 23, it is not greater than or equal to 43. The last value is 43, so yeah, 43 is greater than or equals to 43. So now we've done all of the evaluations for the department ID and we have had a positive match on the last value. Now we still have to evaluate the ID column. So the next evaluation function is going to be, is 23 greater than or equal to 20? Yes, it is. So we can follow along the reference to the next node. There we start with the lowest value again, which is here. So the next evaluation is going to be, is 30 greater than or equals to 43? No, it is not. Is 43 greater than or equals to 43? Yes, it is. So here again, we still need to evaluate the value for the ID column. So the evaluation function goes as following. Is 2 greater than or equals to 20? No, it is not. So we go to the next value of the department ID column, which is also 43. We know that this is greater than or equals to 43. So here as well, we still need to do the evaluation of the ID column, which is the following one. Is 23 greater than or equals to 20? Yes, it is. We can follow the reference and boom, we have found the leaf node. The next step of a lookup is called following the leaf node chain, also known as an index range scan. This step only happens when there is more than one possible result. This is actually a pretty self-explanatory step, because what basically happens is that the lookup goes from one node to another, in order to be sure that it has all of the valid results. Imagine that we end up in this leaf node. How would the lookup otherwise know that it has all of the possible results without going to the next node? Pretty simple, right? That's basically it for this step. But you should remember that hopping from one node to another node has a small time cost. Let's visually recap that last step with an example. So like I said, we are looking for all of the employee values where the department ID is 3. Imagine that we end up in this leaf node after traversing the index tree. Now we can already tell that the next node also contains a valid result, but the lookup doesn't know, so it has only one choice, and that's to hop to the next node and check. The final step of a lookup is accessing table data. There's one thing that you should know about table data, and that is that table data is like ants in an ant farm. It is everywhere. Table data is scattered throughout storage. So whenever you're working with databases and you're looking at table information, then you're actually looking at a visual representation. Behind the scenes, the database has been really busy putting all of the pieces together. Luckily for us, the leaf nodes contain the actual reference to the table data. So all of the matching results of the query, they know where to fetch the rest of the data. And it goes without saying, but I'm going to say it anyway. Whatever is being returned, that depends on what is in the select clause. Aren't indexes awesome? Yes, they are, right until they become slow. So let's have a deeper look into the weak spots of indexes and lookups. Where does a lookup lose time? Here we are again looking at the 3 steps of a lookup. The first step is the fastest one. So traversing the index tree almost goes instantly. Thank you very much, balanced search trees, because that is your superpower. Now the first point where a lookup might lose time is at the end of the first step. It's where it needs to access the leaf node chain. So we know that a lookup needs to hop from leaf node to leaf node in order to make sure that it has all of the matching results. We also know that there is a small time cost involved to hopping from node to node. So the closer a lookup gets to the actual result in the leaf node chain, the better it is. And this is entirely up to the structure of the index B tree. The second point where a lookup might lose time is during the second step, is during leaf node traversal. Imagine you have a composite index, but you can only use the first part to traverse the index tree. The second part of the index is actually a query condition, but for some reason you cannot use the second part to traverse the index tree. In that case, the lookup needs to take an extra step, which is called index filtering. And it takes this index information, which is in the leaf nodes, and it uses it to validate query conditions and to filter out results. Then the last step, where the lookup needs to access table data, is in general the step where a lookup loses the most time, because there is a cost to accessing table data. Now imagine that your query has a condition which is not in the index. That means that a lookup needs to do an extra step, which is called table data filtering. In order to be sure that this data is part of the result set, the lookup needs to access the data to see if it actually matches the query condition or not. Now imagine that you have a lot of possible hits after index filtering or after leaf node traversal, and you need to access the table data for every one of those hits. That's where a lookup loses the most time. These weaknesses, if you can really call them weaknesses, are also known as the predicates. So you have an access predicate and you have two filter predicates. These predicates are actually just conditions that are being evaluated in certain situations. Now, to understand the access predicate, ask yourself the following question. What information or which part of an index can be used by the lookup to traverse the index tree and eventually end up somewhere in the leaf node chain? Or put in different words, the evaluation of the access predicate will determine where a lookup will start a leaf node scan and where it will end the leaf node scan. So this access predicate is a pretty big deal actually. Now the other two predicates are filter predicates, and when you have a suboptimal index, the lookup will rely on these predicates to filter out the end result. To understand the index filter predicate, ask yourself the following question. What information or which part of the index cannot be used by the lookup to traverse the index tree, but can be used during leaf node traversal instead? And then the last predicate, the table filter predicate, is actually the easiest one to understand and the easiest one to spot. Whenever you have a query with a where clause condition on a column which is not part of the index, then the lookup will have to access table data in order to filter out the end result. So in order to understand this predicate, ask yourself the following question. What query condition cannot be resolved by the current index? So these predicates are really important whenever you need to do some performance tuning on a slow query. We have reached the final part of this mini course. This last part will probably surprise you. Heck, it might even shock you. This part is called Things You Wouldn't Expect of an Index. The first thing you wouldn't expect from an index is that column order matters. Now imagine you have the following query. Select everything from employees where age is 36. And the only available index that you have is one on the department ID column and the age column. Boom. This index cannot be used for this query. No way! Why is that? Well, it's because of the ordering priority. Like I've said before, indexes have an ordering priority from left to right. In this particular case, that means that the department ID column has ordering priority over the H column. More specifically, that means that the department ID data in the index tree will be ordered first. The H data in the index tree will be ordered in relation to the department ID data. But since we have no department ID search condition in the query, that makes that the ordering of the H data is useless in this index tree. So there is no logical way to traverse the index tree without any department ID search condition. And that's why this index is useless for this query. A fix would be to have an index on the H column or to reverse the index order. The next thing you wouldn't expect of an index also has to do with the order of columns. Imagine you have the following query. Select everything from employees where department ID is greater than 25 and the age is 36. The only available index is one on the department ID column and on the age column. Boom! Suboptimal index. Only the department ID data is used. Huh? Once again, the ordering of the age data is unreliable. And once again, this has to do with the ordering priority. As in the previous example, the ordering priority is on the department ID column. So that means that the ordering of the age data in the index tree actually depends on the department ID values. Let me put that differently. You only have a sensible ordering of age data in the index tree when the value of the department ID is the same. And you can see that clearly right here. Here we have a bunch of identical department ID values, and thus the ordering of the age data actually makes sense. But when you look at the entire leaf node chain, then we have multiple different values for the department ID, and thus the ordering of the age data seen over the entire leaf node chain doesn't really make that much sense. And that's exactly the case that we have right here. We aren't looking for one department ID value, we are looking for a range of department ID values. We are looking for everything that's greater than 25. And thus, the lookup cannot rely on the age data or the ordering of the age data to go through the index tree. Maybe a small example will help make things more clear. Let's pretend that we are the lookup, that we are going through the index tree. So we're going to follow and do all of the evaluations that a real lookup would do. And we've done this before, so you should be able to follow along quite easily. The first evaluation that a lookup would do when you start right here is evaluating the department ID data. So that would go like following. Is 30 greater than or equal to 25? Yes, it is. So the lookup would go to the evaluation of the age data. Is 30 greater than or equal to 36? No, it is not. So the lookup would not follow this lead and go through this and not go through this leaf node, and it would miss out on a valid result. Do you see in this case why the ordering of the age data is unreliable for a lookup? This is a perfect example though of a lookup that would have to use an index filter predicate. It's because the lookup can only use the first part of the index. However, the age data is actually there. It's in the leaf node chain. So what would happen is that the lookup would use the department ID condition as the access predicate, to access the leaf node chain. And then for every matching department ID value, it would evaluate the age data and see if it's a match with what we're looking for. So whenever you are creating an index for a similar query with a performance issue, remember the following. In the index definition, always put the columns that have an equal conditions before the column that has a range condition. Because everything that comes after the column with a range condition cannot be used by a lookup to go through the index tree. If you happen to have a query with two columns that have a range condition, then you cannot have a fully functional index on both those columns. The next thing you wouldn't expect of indexes is about composite indexes. Consider the following composite index. It's an index on the department ID column, the age column, and the first name column. You can use this index for a wide range of queries. Really? What queries are you talking about? Let's have a look at some examples of queries where this index might be useful for. Now, when we look at these queries, there is no real big surprise in there, right? Except maybe for this third query, which has a range condition on the age column. Now, for this lookup, it's not really a big problem. Why? Because the other search condition is on the department ID column, and it's an equals condition. The department ID column comes before the age column, and that's why for this query, this index is still a good fit. Let's have a look at some queries where this index is not that useful or might not even be usable at all. In the first query, we have a search condition on the department ID column and on the first name column, but not on the age column, and that is why this index is not that useful for this query. During lookup, it will only be able to use the department ID to go through the index tree, and later on it will have to use the first name as an index filter predicate. Now, looking at the second query, we see that it has a search condition on the age column and on the first name column, but not on the department ID column. So this index is not even usable for this query because there is no logical way to start going through the index tree. And then the last query, well, we've seen this example, right? There is a range condition on the department ID, and the department ID happens to be the first column of the index tree definition. The last thing you wouldn't expect of an index is a neat trick called covering indexes. Consider the following query. Select first name from employees where age is 32 and department ID is 43, and you have an index on the columns department ID, age, and first name. Boom. This kind of lookup is the fastest lookup around. Why are covering indexes so flashy and so blazingly fast? It's because they contain all of the required data in the leaf nodes. So that means all of the data for the search conditions is in the leaf nodes, but also the data for the fields that make up the end result. There is no need for a lookup to access any table data. It's all there in the leaf nodes. And that's why covering indexes make for the fastest lookups around. We have reached the end of this fast-paced mini course, and I have to end with an acknowledgement. Practically all of the information in this mini course comes from this book, SQL Performance Explained by Markus Winand. Especially the drawings of the indexes are very heavily based on examples from this book, but I did draw them myself because I always learn more when I do stuff myself. This book is a recommended read if you want to know more about SQL performance. Thank you all for watching, and I hope you learned something. Bye!